Okay. So there's nothing else from the test. We're going to jump into new stuff. Okay. We had that one section from chapter 4 to do at the very end. And it's something that I sort of was leading us up to with a question from the very first test, I think it was, where I said, if you knew the second derivative, could you work back to the first derivative? There was a bonus question that was like that. And that's, incredibly enough, one of its names, that process of finding the opposite of derivative is called the antiderivative. It's crazy. That's the lesser used word for it, but that's the word we use for right now. It's a little graveyard of markers. I have 3 black markers to see.
4-9.
Yeah, 4-9. So we should be at the point where I could tell you this. I could say f prime is cosine x. So what would f of x have to be? And you got it. Now here's the beautiful thing about derivatives versus antiderivatives. You have to think backwards. Sine's derivative is cosine, right? So that's fine. If I would have said f prime is sine, f of x would have had to be negative cosine. So you write down what you think it is, and then you just kind of, no, that would not be right. It'd have a negative sign. I don't want it, so let me put that there. You guys semi with me? So it's really just building off of, we know all these derivatives, we should be able to just go backwards a lot of the time. Now, it's not always that simple. Because antidifferentiation does not have a lot of the same rules that derivatives have. Derivatives you can really sink your teeth into and just attack almost any problem you're given. You can just apply product rule, chain rule, all this kind of stuff. Integrals takes a lot more craftiness. Right? So we're going to slowly learn, first off, what the hell they are. And I just said the word, didn't I? So the word that's more often used for antiderivatives is called integrals. So one thing I really want to show is 4-9 is all about just straight up. We're not going to call any weird words yet. It's just the opposite of derivative. So just think backwards. And then chapter 5, we get into what the hell is an integral. And then I want to try to show you, this is not always true, but the integral is almost always equal to the antiderivative. So that's kind of like a roadmap of where we're headed. So this is pretty damn simple so far. There's one little problem though. I mean, this is true. If I take the derivative of sine, I do get cosine. But is that the only thing that could have been here to lead me here? And all you guys are going to be like, well, of course, Jeff, you're crazy. But there's one thing that derivatives do that wouldn't show up here if they were here. Constant. And what could that constant be? Anything. So we normally represent it, because we're really creative in math, the constant we represent with a big C. And that's the thing. You're going to know what I mean in approximately 2 weeks. You're going to know exactly what I mean when I say it's really easy to forget your C. We get so focused on the main thing, we forget that we have to put that, what seems like an arbitrary thing, but it actually helps us capture the right function. So what does a derivative really tell me? If I know the derivative is sine, that means that its derivative looks, of course, like this. But does it tell me, and I've said this before, that's the shape of it. I know the shape of it has to be like that.
It doesn't tell you the place.
I love it. So I have said that enough. It doesn't tell you where the hell it is. That's what this guy does. He kind of tacks it to a position. You with me? So at 0, the function better equal C. Or if you're told that f of 0 equals 2, well then C would have to be 2. to make that actually fit right there. Okay, maybe. So it's not just an arbitrary thing that we throw in there because maybe it could be there. It's actually to help us capture where I want that function to be. Okay, maybe. So something a little more interesting then. What if I had... Let's kind of capture that that earlier bonus problem. If I told you that f double prime was, what you got there, Jeff? 48x squared plus, who knows? You could do it maybe 42x minus 7. I like it. What would f prime have to look like?
16x cubed.
I love it. So you know that this came from a cube, because it's currently a square, and thinking backwards, it would have come from a cube. And then what you do is you suck that 3 back up out of the 48. You with me? So what you're really doing is you're saying that kind of thing, right? Because that 3 would have come down to make it 48. So what must have been there before? 16. Now keep going. What about this guy?
21x squared.
21x squared.
Minus 7x.
Minus 7x.
C plus C.
Good. Plus C. I like it. And then so what's f of x have to look like? What would this be? X to the...
4x.
Good. So it must have been a 4 out here. So when that 4 comes down, it makes it 16.
7x cubed.
Good. This would be x cubed. A 3 would have come down, making it 21, so there must have been a 7 there.
Negative 4.5.
Don't go there. Give me some fractions. This would be x squared. When I take a 2 down, and actually, you just keep in mind, it's just going to... You with me? Keep going. Cx. Good. And we just keep... When we get another constant, we can either call it C1, C2, C3. That would be more like in differential equations. You do that a lot. Here we're going to use big C, big D, big E, big F, whatever the hell we can use. So how's that feel so far? I mean, that's, if you understand differentiation, you understand derivatives, you should be able to tease out what the antiderivative is. You've got to shift gears, and sometimes it's really easy to shift gears in the wrong direction. For example, what if I had... Oops, Jeff. Don't say anything out loud. Think about it for a second. Or for several. After you get this, we'll talk about our first general integral rule, which I forget if they even have in here. No, they don't. Yes, they do. Sweet. Okay, good. So who thinks they've got it? Oh, sorry. So let me kind of help you guys out. Let's look at what the general rule would be. So first off, recall x to the n, the derivative of x to the n, what happens?
X to the n minus 1.
Yeah, n comes down, and you get x to the n minus 1, right? Okay. So now for the antiderivative, don't really have a symbol for it yet. But if I say f prime is x to the n, think backwards. Basically do everything backwards from this rule. Right? So instead of multiplying by n, now we got to be a little careful. Let's take a specific example. X squared. Where would that go? That was f prime. What would f be? What would it be based on? So see, you always start with, that would be based on x to the n plus 1. I love it. You have to start there just to see what was up there. So when I took the derivative, the 3 would come down, but there's no 3 there. So I have to also divide by 3. So it'll kill that 3 that would come down. So that's that forward thinking. We're doing a backwards operation. So we're thinking, we're kind of going backwards and then going forwards a little bit and then adjusting things. So if I were to take this guy's derivative, I'd be completely wrong. Shit, I'd have a 3 here. So I just put it over 3. And of course I also put plus. So here, if we figure out what the power would have been, I divide by that power. Sorry, who do I keep ignoring?
Can you explain that one more time? Kind of lost where you go, the over 3, the x to the third over 3, where how you went from x squared and why you made it divided by 3.
So if I did have x cubed, what's its derivative?
3x squared.
3x squared. But I'm saying I don't want that. I want the derivative to be this. So what can you do here to make that 3 not show up here?
Oh, no, those 3.
So now what happens when you take this guy's derivative? F prime would be... So another way to look at this, of course, is 1/3 x cubed. Is that cool? So f prime would be 1/3 of 3x squared. The 3 doesn't show up. Yes?
Is the answer 15 e to the x?
Well, let's see. So now let's use our newfound understanding. So I have 2/5. This would have come from what? X to the... Good. So I divide by... Actually, let's be even smarter about this. I would divide by -3/4, which means multiply by -4/3. And then I just kind of clean this up. -8/15. And of course, plus c. So it's pretty easy when I say 48x squared. I think everybody, no questions at least were asked. I think we all kind of got that. Because there was a 3 there to get sucked up. But if there is no 3 there to get sucked up, I have to put an over 3. And that's really what I did. I put an over 3. That's why it became 16. I divided by 3. Alright, cool. It kind of makes sense. The opposite operation of bringing it down, multiplying by it, and subtracting 1 should be adding 1 and dividing by it. That's the inverse operation.
Yeah.
Okay.
So in this case, yeah. That 2.
So now you have to add 1 to this, right? That's how we got to there. And wherever we go to is what we divide by, or in this case, multiply by the reciprocal. Cool. Yeah, we feel so far. It got a little worse, but not terrible, because now we have a rule we can always fall back on. Okay. So, what if I had... Oh. So now we know now, just looking at the rule, what's the one time this rule does not work? What can you not do? Yeah, exactly. Because you can't divide by 0. So if n was -1, right? Not -1 factorial, by the way, if you know that. Just negative. No punctuation. So what the hell? Well, what function would that be if n was -1? 1 over x, right? But we know that guy. Where's that derivative come from? I love it. So the one thing you have to be careful about, and I think I said this when we first did the derivative, closing the door doesn't do much because they have vents in it, but oh well. So I know that I've got something that rule doesn't really cover. That's the one place the rule doesn't cover, but it's okay because I know exactly what the antiderivative of this must be. Say it again. Natural log. And the one thing you have to be careful about, if I write this, of course putting my c in there too, so you know that's not the mistake I made. There is one little mistake I made. I love it, because this function works. What's the only x this function does not work for? 0. So I can't suddenly have my original function having a problem at more places than that. Does that kind of make sense?
Yeah.
So right now this is a problem with everything 0 and below, so I have to put that in there. And that is something so easy to forget, because so often we're only concerned with above 0. We do enough of those and you forget that the absolute value has to show up there in general. Does that by itself make sense? Just making sure that my domain doesn't suddenly suffer just because I did something like that to it. It shouldn't affect the domain. Yes?
If you had like ln 2x, you found the derivative of that, doesn't that come out to 1 over x anyway?
Yeah, it does. And there was a problem on the test that had that in it. I think it was the Newton's method one for a few people. The really funky thing about ln, if you really think about what this means, I'm using g because I've used f enough. If I had ln of constant x, its derivative, and this is what people forgot. People just put this. You remembered that it's 1 over that, but what did you forget? Chain rule. You forgot the inside gets a term, right? Times a, because that's the derivative of the inside. A's cancel. No matter what constant I put in there, the slope has the same shape. And if you really think about that, it might keep you up at night, but or that might just be me when I first learned. That's really funky. You put a billion in there, natural log of a billion x. The derivative is the same as if it was natural log of x. That's neat. So, are you worried about going backwards then or something? Or
How are you going to know what was in front of the x? Give you anything, maybe.
Yeah. So that's kind of like from context possibly, but in general we have to say that this is true. But if you're worried that, what can I say here? This doesn't come up too often unless you want to force something in there. Oh, exactly. It's been a while since I even thought about this. This is the funny thing about it. Here's why this is true. And this is so funny I didn't even think about it until now. What's the natural log of a product? Any log of a product. How do you do the log of a product? It's the log of one plus the log of the other one, isn't it? So isn't this a constant? So if my function actually should be a billion x, my constant will capture it. Cool. God, I haven't thought about that in so long time. Because you don't even really realize it, to be honest with you, Sam. You don't even realize that the constant, you can write it as the natural log of something and then put them together. Why would you ever think that? So it so rarely comes up that you could do that. And then if the constant has what you need, why would you even care about what number should be in there? It's the same function. Because you can always pull them apart. Cool. I like it.
So let's do a concrete example. Not of that, but just of what we're learning.
What, another kind of example?
Never mind.
All right. Oh, a concrete example. Yeah, pretty concrete. Let me see. So if I had f prime of x equals 3 over x, what would f of x have to be? No. You can't apply that rule because you'd have to add 1 to the power and divide by it, so you get x to the 0 over 0. You with me? This is 3x to the negative 1. So you'd say this came from x to the 0 over, oh shit. So that's the one place that this rule does not work. So if you ever see something with an over x in it, it's going to somehow be related to natural log. If you see over x plus 7, over 2x minus 8, that's going to be some kind of a natural log. So don't freak out about this. This is just 3 times 1 over x. So what's the f of x going to be? Sorry, that's what you've been saying? Like, yeah, Jeff, listen to me. And of course,
Plus C.
plus c. I knew you weren't done. You with me? And, you know, we got to be careful. I should really reinforce this. You got to put that absolute value in there if you don't know what x's you're using. Okay. I've just gotten into the really bad habit of not caring unless I know my problem cares. Then I care all of a sudden. Okay. So there's a couple other ones. I mean, we really can't, until we get into the nitty-gritty of the rules of how to apply this to something, we can't go beyond functions I exactly know or just constant multiples of them. So what do I mean by that? I mean, if I put up here h prime is 2 secant squared, what must h be?
2 tangent.
Yeah, because I know secant squared comes from tangent. So I mean, this whole section, don't even let it be difficult. It's really just, if you can think backwards about your derivatives, then you really know them, of course. You know, if you need to do it backwards and forwards. So really, this section, I think they put it in this chapter just to really reinforce all the derivative rules, because you have to do it backwards and forwards. So this, like you said, would be 2 tangent plus c11. Cool. Cool. All right. Let's see. Is there anything else major here? Blah, blah, blah. Of course, one of the coolest ones. What about this? F. Oh, sorry.
The 2 tangent is the tangent to x. The 2 secant square x, right? It's come from 2 tangent to x or no?
No. Here's a really big key. Only, in fact, I'll make this one. Let me remember what oh yeah, okay. So let me change my idea here. So what if I had, I can never change the inside of a function by derivatives or antiderivatives. You should know that by now, because the chain rule says, take the derivative, leave the inside in there, and then the inside gets a turn. So if I don't see a 2 inside there, there was not a 2 here, unless there's some crazy trig identity I can apply on top of it. Does that make sense? So since this has a 2 in it, and of course I could use a trig identity here, but since this has a 2 in it, I know it would directly come from something with a 2 in it. And I just have to be, oh, this should be prime. So where would that have come from? Well, directly would have come from, and then worry about the adjustment. Always the constant is just the adjustment due. The most important thing is what's the core? What's the function it came from? It came from cosine 2x. So now how do I have to adjust it 2 ways? I like the 1/2. If I take the derivative of cosine, I'm going to get negative. Do I have negative sign? Shit, so I better have 1 there so it will disappear once it comes in.
Why did you put that 1 in? Oh, so that 2 will...
Because I know, and I really hope you guys are starting to understand, I know a 2 would come out. That's the chain rule. It doesn't really come out, but this is a quick way to say it. Chain rule would have a 2 come here. I have to put a 1/2 because I don't want a 2 there, right? So it's not really the same exact rule as a power rule, but we saw stuff like this that looks like power rules in a way. That thing comes out, ease, the thing comes down. You with me? So it sort of feels like power rule. Yeah.
When you say you don't want a 2 there, why don't you want a 2 there?
Because there isn't one.
Oh, you don't want a 2 there.
So I already know what the form should be once a derivative has been applied. So if I don't have this, this derivative would be negative 2 sine 2x, right? So then I basically just divide by negative 2, just so it won't be there. Cool. then if we use our favorite function, and I'm not being sarcastic, believe it or not, for once, if that's the derivative, what must the function of it?
Negative 1/5.
I like it. So E is going to come from itself, right? You start there. And then you know a negative 5 would come down for the chain rule, so what do you have to put here? Negative 1/5. I love it. Same kind of thing as this. It's very similar, because chain rule is what applies to both. That's why it's very similar. All right, cool. So, just so you know, there's a purpose for the rest of the book. If I gave you something like, oh, what do you got, Jeff? Yeah. For example.
This is part of the section we're working on, or
This is one of the last things we'll do in this class. This is the last section we do in this class involves this kind of problem. So I just want to show you, this is the ultimate place that calculus gets to, is how to anti-differentiate this function. And we can't currently do it directly. Some of you guys might be able to tease it out, possibly, but it's not easy. There's nothing direct about it. But that, I just wanted to put that there, just so you know, that's our goal. Not everything can be done directly like this, because not everything's, and then we have stuff beyond this class, which would be stuff like, what you got, John? Stuff like that. We're not going to be able to do that. I can't remember now. I don't think we can do that yet in this class. So forth. I mean, there's a ton of them. You write down just an arbitrary function out of somewhere, you probably can't anti-differentiate it as easily as any of these. It's going to have products, and there is no real product rule for antiderivatives. We kind of do something really creative to get our way around products when we try to do antiderivatives. Okay, let me not freak out too much. Why change things now, Jeff? Okay, so that's section 4.9. Let me give you one last type of problem, a little more specifically. I sort of did this kind of problem earlier, but let's make it a little more formal. Here we go. This is problem number 36 in the book. If you want to look at it. So there is no quotient rule for antiderivatives. But thankfully, what can I do with that?
Extra negative 1 put on top. You make it.
Yeah, but even better way to look at it.
Factor the top. And then.
Cool. Just divide each piece by x. Split it up. Now, why did they tell me all this crap over here?
So you find out the constant.
Yeah, good. And they gave us 2 points. We'll see why. I'm not sure either. We'll find out why that is. And I think I figured it out. So, what's f going to have to be then?
One half x squared minus ln x.
Minus ln.
Whatever. Let's see.
I like it. So you can draw on the air, that's fine. I'll go with that. Is everybody cool with that so far? Right, and you'll start to do this, like, you'll get to a point where if I say x to the 7th and I want to do the antiderivative, that's going to be 1/8 x to the 8th. I mean, The 1/8 is 0, they kill the 8, that would come down. Cool, that's the quickest, easiest rule to get down. Of course, they can't all be polynomials. So now I want to apply that, and of course, if I forget this, that ain't going to make any sense. But let's try to apply this. It says f of 1 has to be 1/2. So f of 1 equals 1/2, 1 squared, minus ln of 1
So
plus
that's how you
c.
find your C.
Huh?
Whatever that equals without the C, you plug in what that C is going to be. Does that make sense? You're going to set it equal to 1/2, and subtract whatever that number is, and that's going to be your
Well, I know that f of 1 is 1/2. So then I can, so I get 1/2 minus, and of course, what's ln of 1? 0. Plus c. So c looks like should be
0.
0. Plus c. Now, what's f of negative 1? Now, let me see. Let me make sure. Yep. All right, let's see what happens. So what's f of negative 1? 1/2 negative 1 squared minus ln negative 1 plus c. You guys with me? Is this okay? All right, all right. And then what do we get here? We get f of negative 1 is 0. I get 1/2 minus 0 plus c. So c has to be negative 1/2. So I need to figure out why did they give us two values? Did they mean that to be a second derivative? Yeah, I think that's a typo. Good work picking a typo. Why would it make sense that I'm going to need two statements like this if it's a second derivative? Because every time I antidifferentiate, I'm going to pick up a constant, right? You with me? Like we did earlier. We had a second derivative. We did it once. We got c. We did it again. We had a cx plus d at the end. So I have two unknowns. I would have to have two pieces of information. So I think this is a typo. But I saw it and I was curious. I wanted to see what it would lead to. And it leads to a contradiction, right? So I think they meant this to be a second derivative. So let's try out one of those and see what that looks like. So if I do like number 41, be very careful. I'm going to see how far you guys can get. Notice they tell you something about f prime, and they tell you something about f. So you want to apply those at the right moment. See what you guys can do with this. And you start to realize the evilness that is derivative sign is negative cosine. But the antiderivative of cosine is sine. You got to be careful. Oh yeah. me try to catch up to you guys a little bit. What must f prime of theta be?
Negative 1/2.
Negative cosine.
Yeah, because cosine would go to negative sine, so you have to have a negative there. I like it. But sine is cool, right? Now, I don't have any 2's anywhere. There's no 2's that would come from somewhere, so I don't have to put a 1/2 to counter the 2. If there was a 2 inside, I'd have to put a 1/2 there to counter it from coming out. I'd kill it right when it came out. And of course, good. So the whole reason they gave me all this stuff is for this. Right now, I can apply that second thing, because it works on the first derivative. So I know f prime of 0, which is, good, cosine of 0 is 1, so negative 1 plus 0 plus c, I know that that is 4. So c must be 5. So then my f prime of theta is negative cosine theta plus sine theta plus 5. How are we doing so far? Cool. I like that. And then f of theta, good, negative sine minus cosine 5 theta. I love it because my variable's theta, so be real careful. Good. And me personally, I have no problem with reusing C's, but you might run into some teachers that will have a problem with that. But it's just, to me, it's just a middleman thing. For right now, I need it just for right now. F, and then what do I use? Yeah, f of 0 is 0. So negative 1 plus 0 plus c, and that of course is 3. So then c in this case is 4. I like it. So then f theta is wherever. Negative sine minus cosine plus 5 theta plus 4. Yeah, thank you. I lost track of it. So to check yourself, you would just do 2 derivatives on this and make sure it comes out to that. Right? Of course, after 2 derivatives, these are going to disappear. And after 2 derivatives, trig functions repeat, but they become a negative of themselves. So sine, 2 derivatives later, would be negative sine. So, I mean, you can pretty much see how that's going to become that pretty quickly. Okay, how's that feel so far? We call this, in general, we call this thing, this idea here, we call it initial conditions or boundary conditions. This is more generally physics and stuff. This is more specifically for like quantum mechanics and stuff like that. But you can use it in other cases too. Right. But initial conditions is basically, I mean, this is what it is at 0, This is what it is initially. I forget what this book calls that. Oh well, I won't find it real quick. So what I really want to focus on, that's section 4.9. So that's really, again, sort of a way to truly understand derivatives. You can do backwards and forwards, you really understand them. We're going to, chapter 5, we're going to do something that seems very unrelated, but then I'm going to say is exactly what we just did. It's going to be a little bit interesting going into it, realizing that. So everybody got this here? So, how in general, let me ask you something that's kind of interesting. How would you, let me ask you kind of a stupid question first. If I had this shape, and I knew this was square, base, with a triangle on top, let's say this is 7, and let's say this height is 5. Alright, little house. How would you find the area of that shape? Exactly, so I sort of did it for us. We kind of naturally, if I just gave you this picture, you would draw, you'd break it up into shapes that you know the area of. I have no idea what the area is of this shape. I have no formula for that. So I cut it into shapes that I know. Right? So that we could do, that's easy enough. Has anybody ever seen for a circle how you can do that? If you didn't know the area of a circle, you can actually cut it into a shape that you do know. Have you ever seen that? It's kind of neat. You would cut it down here. Then you would do like, what do you call it? This little, when you cut it and you open it up, it's like connected still. So you cut it out, but you don't cut it all the way through the circumference. And then I can open it up. How are we doing so far? You guys kind of with me? So you cut it down the middle. So that's separate. Cut it, but not all the way out to the end. I still have it attached there. You with me? And if I open it up, it's going to look like the top part of some jack-o'-lantern mouth. Right? It's going to look like that. Really bad. But go with it. It's fine. Now, if I do the same thing to the bottom and I fit it in there, it's going to be approximately, well, it's actually going to be a parallelogram. But when I teach this, I don't really tell them that. Just tell them it's a rectangle. But this, what is this length here? Close? All the way around is 2 pi. I took this and opened it up, right? So it's pi. And what's this, especially if I make a lot of triangles, what's that going to become? Radius. So then, of course, what happened here, Jeff? Oh, I mean something. Pi r. Circumference is 2 pi r. So halfway around is pi r. Cool. So that's pi r, half the circumference. R down the side. So, of course, the area of that rectangle, pi r times r, pi r squared. So that's kind of a really rough proof of the area of a circle by cutting it into shapes that we know. How are we doing so far? You're all like, okay, that's nice, Jeff. I have no idea if this is anything related to calculus. But one giant thing calculus wants to do, so it finds rates of change. That's what we've been doing this whole time. But now we're getting into the other thing it does, which is it finds areas. So what we're really working towards is if I had a function that looked like that, and I want to know the area here, below that function from, let's make this a little more arbitrary, from A to B. I want to know that area under that function. And the area really is, I mean, if I have, this is y, this is x, that area, of course, would be x, y. That's incredible. Right? So if, let's see, how do I want to put this together? If this one, I'm trying to jump ahead a little bit, and I just decided not to. So, if I know the rate of change of something, if I know I can write 80 words a minute, you with me? How many words can I write total after 5 minutes? 80 times 5. And what does that really relate to? That would be like, here's 80 words a minute, right? So after 1 minute, it would be at 80, and so forth. So after 5 minutes, where am I at here? No, I'm sorry, I'm jumping too far ahead. So here's 80 words a minute. And I want to know after 5 minutes, how many words will I have written? That's 80 times 5, right? So if I graph the rate of change, and I find the area, I'm actually getting an amount of something. Right? So if I know it's changing by 6 cubic inches per year, then if I kind of graph the rate of change and I go over a certain amount of time, I can see how much it's actually accumulated over time. I'm thinking about that stalactite problem again, right? How large is that damn thing now? You with me? So antiderivatives is a way of collecting what derivatives tell me happen over time. Did that phrase make some sense? A derivative would tell me how fast I'm doing something, or how quickly something's changing. Finding the area, and actually what these integrals do, is they tell me if I wait a certain amount of time, what will that accumulate to? Yes?
So, with that stalactitis problem or whatever, is this another way to, you can find those same answers without using related rates? Or
It would be
different information?
a problem that was kind of worded in reverse.
Okay.
Really, It'd be another way to use those rates of change that I was given, is another way to say it. Right, so they're related. They sort of they go in opposite directions. So on that problem, I was completely concerned about how much is this thing changing over time. Right, so I was completely concerned about derivatives. If I start giving you rates of change and I said, well, after 7 years, how big will it be? That would be this. That's going to say, I know how quickly it's changing over time. I want to know over a certain amount of time, how much will it actually grow? Okay, maybe. Sweet, okay, maybe. So coming back to this. What we can do is we can do like we did with the circle, believe it or not. We can cut this thing into shapes that we know. And this sounds weird, because you're thinking to yourself, there ain't no damn way. But if we allow ourselves to approximate the answer, that will make this a lot easier. You with me? So another way to do this problem would be filling it with little squares whose areas I know. And then seeing about how many squares does it take to fill it. You with me? That would be an approximate answer to the area of that circle. What would make my approximation better? Smaller squares. I love it. Right? So if I break this shape up into rectangles, where the rectangle's height is controlled by the function I'm given, what will that end up being? So if I say, now here's where I'm going to get a little more technical. I'm going to say like left endpoint. What that means is I'm going to have the left endpoint tell me how tall my rectangle is. Right? So the first rectangle I could draw would be like that. And then the next one would be here. It would be this tall. What did I just say, Jeff? The left endpoint. It would be this tall. I have trouble with left and right. Okay. And then the next one would be that tall. See how it overdoes it a little bit? You guys a little bit with me? And of course,
overdoes it and underdoes it, it's going to...
Yeah, if my function's kind of going up and down, it might average itself out. If my function is kind of always increasing or decreasing, I'm going to under or overshoot it all the time. In that case, what could I do? I could change my rectangles unless I really don't want to. And what if I don't really want to change my rectangles? I can do a left endpoint and a right endpoint and average them. And you said it. I love it. I didn't have to tell you that. That just makes sense. If one way would undershoot it all the time and the other way would overshoot it all the time, I'd get a much better approximation by doing it both ways and averaging. Or there's even one more way to do this, not left endpoint, not right endpoint, but midpoint. Don't even go there yet. That's Simpson's rule. That's way in front of us. We're not too far in front of us. I think you got to get this idea. You would just, the left endpoint tells me how tall this thing is. So it kind of looks like, I don't know, it kind of looks like it undershot it maybe a little bit more. Well, maybe it came out about right. How many rectangles, well let's see, what would the relationship be between how wide each one is? So to make this a little easier, we're going to assume that our widths are always the same. In general, they don't have to be. And normally in mathematics, what we do is we assume the widths are the same. We lead it all the way up until we get to the point where we're really doing what's called integration. And it's sort of going to be like when we had to go through the limits. Remember that? Limit. And we finally said, okay, let's just do some derivatives. Learn some rules. You with me? So now it's going to be rectangles. Rectangles, maybe some trapezoids. And then, okay, let's just do some intervals, right? But we have to go through this to see what really goes into building these things. What would tell me how wide a rectangle needs to be? Two things I kind of have to know. One of them I already know. I put it up here, but the other one is also up here. But, okay, good. So the number of rectangles.
And you need to know how far, like how...
Beautiful. Distance, which in this case would be... I love it. So if I took the distance, total distance that I want to cover with rectangles, b minus a, and I did what with that, I would get delta x. I would get how wide each one has to be.
divided by n.
Yeah, so if I take delta x would be the width, how wide each one has to be, is how far I want to go, divided by how many rectangles I want to use. you've ever taken statistics, this might sound familiar. This is sort of like, what am I thinking about? Z-scores, sort of like, what is that in my head now? Too bad. Does that make physical sense? And when I teach this, it's sort of like when you build a histogram in stats. I think some people were kind of agreeing. You do the same thing. A histogram is rectangles. So when I teach that, I say, let's say you want to put wood paneling all along this wall, right? You just feel like going for a retro look or something. And that wall, let's say it's about 25 feet long. And you want to put 10 boards up there. How wide would each board have to be? It's a very physical problem. You can imagine that happening. You can see me putting the boards up there. So if it's 25 feet long, and I want to, and what did I just say? I want to use 10 boards. How wide would each one have to be?
2.5 feet.
Yeah, you take the distance divided by the number. The distance divided by the number. I mean, that's a very physical problem. You got to love it, right? In math, it looks freaky. But math is just trying to capture the general idea of what it means physically. Cool. Cool. All right. So, let me go further. Now, I know somebody's hoping for a concrete problem. We're almost there. So the approximate area, in fact, I would call it AL. But I'm going to have to use what the book calls it, LN. I would like to call it area using left endpoints. But just to be consistent with the book, they just call it left endpoint with whatever. I'm with it. In general, LN, let's see if you guys are with me. And here's, we call this one X1. We call this one X2. X3, so forth. Is that cool?
So you need to use notation type of thing?
Oh yeah, we're slowly building up to it. You guys with me? So in this case, since I'm using left endpoints, I would start there. If I was using right endpoints, my X1 would be here. You with me? But it kind of evens out because the last one, this would be X5, X6, X7. X8 would be the last one. Poor little B dude gets left out, right? But if you used right endpoints, it would shift the other way. You guys semi with
I didn't get that part. You said everything.
Well, right here, if I use left endpoints, I'm actually using A as a determiner. How high is this going to be? What's this height right here? F of X1. Or in this case, F of A. You're right, because I actually use that endpoint. You with me? And now how high is the second rectangle? What's the height of the second rectangle? F of X2.
Oh, that's where you start your right.
We're still looking at
And
that.
that
We're
would
not
be
looking
O.
at the derivative yet. This is still the function of x.
Well, and
It
again,
doesn't really matter.
I always think of it as what we're doing is we're anti-differentiating. And that's what I'm going to continue to say that even though the book hasn't made that connection yet. We are finding areas under some function.
Okay.
If I look at this function as if it's a slope, as if it's the derivative of something, I would end up with the antiderivative of it after I do this process.
Okay.
Or something related to it at least. So let's see if we're there yet. Let's see. So the approximate area, which the book uses a big ass L for. I wish they would use AL, it just makes more sense, but too bad. I can't remember if I used this symbol in here yet, but I'm hoping you all know that symbol.
Sigma notation.
And that means summation, right? So it's a real quick way of saying repeated sum forever. So if I said 1 plus 2 plus 3 plus 4 plus 5, you just say sum I equals 1 to 7. If I wanted to go up to 1 plus 2 up to 7. Right? So 1 plus 2 plus 3 plus 4 will be the sum of I equals 1 to 4 I. Let me just let that sink in. Some of you guys might not have seen that notation before. We're supposed to teach that in pre-calc. Sometimes you don't quite make it that far. All right. So here, what I want to do is I want to add up all of the areas together. That's the whole idea. I want to break this thing up into areas I know. If I add them all up, that should be approximately right. Might undershoot it, might overshoot it, but it should be decently close. Unless you use one big ass rectangle, then I'll be way off. So what's the area of that first rectangle, for example? Let me not do the summation here yet. Let's hold off on that. What's the area of that first rectangle? How wide is it? Delta x. They're all delta x wide, right? How tall is it? So it's f of x1 delta x plus. How tall is this one?
F of x2
And how wide is it?
delta x.
So it's f of x2 delta x. So thank God we have a symbol, because I don't want to write on anything out, because it's the same stupid thing over and over. The only thing that's changing is the subscript to move me along, right? So to write this better, I say it's the sum. In this case, it's going to be I equals 1 to 8. Is that cool? Okay, I'm going to assume that's a good... f of xi, because that's what's changing, is the height. So when I is 1, it'll be f of x1. When I is 2, it'll be f of x2 times delta x. So it's just the height times the width. That, of course, is going to give me the area of each rectangle. And if I add them up, that's what that means. Greek letter S. So we thought it was a good thing to use for sum. So that means sum the areas of the rectangles. I'll get the approximation for the area under the curve.
The change at x is going to be held constant, right? It's going to be the same for all of them.
And it doesn't have to be, but we're going to do that.
How could it not be? It's still have the same.
You could do anything. You could... let's see. Do I have a different color? This poor picture, I think I've done enough to it, but maybe not. The height... It could be determined by the left end point. It could be determined by the right end point.
No.
Or it could be determined by the midpoint or any damn point in there. That height doesn't truly matter. If I make my rectangles smaller and smaller and smaller, which sounds like eventually we're going to let the number of rectangles be... I want to let the number of rectangles go to infinity. So I'm going to have this being a limit. Then if I let the rectangles that I'm using go to infinity, it really does not matter which point I use. Because I'm going to keep getting less and less to choose from. So if I say I always want to use the point that's 1/3 of the way between the endpoints of the rectangle. Well, my rectangles get infinitesimally small. I'm using it at every freaking point.
So why don't you make that n right there like a big number instead of...
Because I didn't feel like drawing that many rectangles.
Oh, okay.
But you got the idea.
Yeah.
To make this a better approximation, that's exactly what I would do. But there's always that competing thing. If you're approximating, how much work do you want to do? Right? I want the approximation to be good, so I don't want to do like too little work. But it's an approximation, so I don't want to go crazy. Right? Now, eventually, we're gonna do like we just said. We're gonna let n go to infinity and hope to God that I don't have to draw an infinite number of rectangles. Hopefully that's a way we can do something symbolically to give me the answer for what that would be. And that's when we're going to see the connection between this process and antidifferentiation. You just got to trust me. Okay. So right now we have two separate ideas. We have 4-9, which is its own thing, and we have 5-1, which is finding these areas of rectangles. Let this be simple if you can. It's normally the symbols that get in the way and all this crap, and it just feels like you're being so technical when you're really just finding areas of rectangles. That's all it is. So, what I want you to do, let's do something concrete before we all go insane. I think I've got enough of this discussed that this will make sense. You have one over there next to you, I think. Yeah. Right, yeah. Okay. So before I think some of you guys have probably jumped into this, but I want to do the first part together, and I'll let you do the second part. Because again, this is the first time we're looking at a concrete example of this. But you can do a couple of these things. For example, I want to go from 1 to 4. So I've given you more of the graph than you really need, but we want to look at the graph and we want to identify the area we want to find. So I really want to just find the area from 1 to 4. Sweet. Right, here it goes. Poor little dude. Cool? So I'm not going to worry about the fact that we're going to talk later about what the hell would negative area be. If it's below the x-axis, that's negative area. That's neat. I don't have a problem with negative area, but some books do, and this book does. So we'll see what happens. What would the width of each rectangle have to be?
1.5.
Yeah, exactly. So that my width would be b minus a, which is 3. I got to go 3 across, and I want to use 6 rectangles. So each one has to be 1/2 big. So the first thing I'm doing is I want to use, here we go, left endpoint to identify how tall each one will be. So what I'm going to do is I want to go 1/2 of the way. And of course, I don't think I have exactly half there, but it's too bad. So I want to go here and halfway over. And the height is just always going to be determined by how high it is on the left side. So is everybody kind of with me? So the width of each of my rectangles is 1/2. 1/2, 1/2, 1/2. Good. So then I've got this one, and finally this one. All right, how are we doing there? So does this one seem to over or undershoot it more? Yeah, it undershoots it more because on that side I didn't want to make this symmetric because if I went from 1 to 5, it would have been we would have seen what happened. It would have been exactly as much undershot as doing the other endpoint would be overshot. Some of you guys might be able to see that. So here I wanted to make it a little anti-symmetric so it didn't come out too nice. Okay, how are we doing so far? Is that cool? That's not too bad. Drawing some rectangles. Alright, so I've put the little, what it looks like symbolically for the stuff going on here, but when you start to put this together, you want to be kind of nice to yourself. As long as there's not that many rectangles, you can be a little more specific. My first rectangle, how high is it? What's the height?
1.
No.
F of 1.
F of 1. And that might be 1. Let's see. No. So F of 1. And how wide is it? And what's the smart thing we could do? Somebody probably noticed this earlier. Each one of these has a delta x on it. So couldn't I take the delta x? Is that cool? Did you guys see that? So I could do 1/2 times all the heights added up. Right? 1/2 times this height is the area of that rectangle. 1/2 times, what's the next input? 1.5, 11. Yes, sir.
Why are you doing the 1/2?
The width from right up here we knew was going to be 1/2. And that's why I drew it so that it fell right in between 1 and 2, yeah.
And so you just, because it's in each one, you took out.
I love it. So this first rectangle is 1/2 times f of 1. That's the area, right? So 1/2 times f of 1. The second rectangle, 1/2 times f of 1. Why did I do that? Yeah, that's right, f of 1.5. Good job. Plus f of 2. Now you see the pattern maybe, right? Plus f of 2.5, plus f of 3. Just don't go too far. Plus f of 3.5. When do I stop?
4.
You sure?
Maybe.
1, 2, 3, 4, 5, 6.
Sorry.
So see, you always reference your picture. 4 didn't set up this guy's height. What set up this guy's height? And how many of these should I have? 6. I've got 6 rectangles, I should have 6 heights. Yes, sir?
The I equals 1 underneath your E symbol there, though.
Yes.
Doesn't that represent the width? Or is that something?
Oh, no.
On the
What
I
that
side,
means
the
is,
card, right?
when I have something like this, if I said I equals 1 to 6 of I, that would mean 1 plus 2 plus... It starts at 1 and it goes to
Starts at
6.
1.
Yeah.
Okay.
So that just establishes the range that... And we often use the letter I because it's actually called the index of the sum. So, incredibly enough, again, being really creative, people always say, let's use I. So that's what that means, right? So here it's almost silly because it's always going to be starting there. But that's what that symbol means. And now it's just a bunch of plug and chug in the calculator, right? So yeah, you would do 1/2. What's f of 1? Let's see. I could do all the whole numbers here. F of 1 would be 1, is it? Yeah, you're right. Okay, so whoever said that, you're okay. And then f of 2 looks to be -8 plus 12, 4. F of 3 looks to be... Is everybody with me? You guys see what I'm doing? Just exactly what it says to do. Normally it's a good thing. F of 3 would be 18 minus... What is that? 18 minus 13, 5, I think?
Isn't there a formula?
Huh? Yeah, right there.
Oh.
So I know what the function is, right? I know what the function is. So that's what I use to tell me the height. So does that make sense? Is that the connection? I drew that rectangle up to here because it's going to be as tall as the output at 1. The next one's going to be as tall as the output at 1.5. Now if I was doing right endpoints, each one would be as tall as the right endpoint's output. Oh boy. How are we doing? Let this be okay, because this is not that yet. And then help me out with the halfway points here. When you plug a 1.5 in there, what do you get?
2 and 3/4.
What is it?
2 and 3/4.
2 3/4? 2.5?
3/4.
Who?
4 and 3/4.
4 3/4?
And 4 and 3/4.
I like it because then it starts to repeat coming down the other way. I like it. And then you just have to do that. So let's see what we get here. 5, 10, 16, 20, 22, and a fourth divided by 2 is 11 and an eighth, which is 11.125. I don't know. Did I do that right in my head?
Yeah, you did 11.1.
Yay! Sorry. So that's L6. That's the left endpoint approximation using 6 rectangles. That's what L6 represents. You guys do R6. And it should be much quicker because you're going to have a lot of repeat function outputs. You with me? Maybe. So you guys do that one. Oh. Scheiße. You guys help me out when I forget this.
You start with the sides.
Oh, okay.
rectangle. So just make sure you guys are starting off right. So in the first one, the height, I started at my first endpoint, went up to its output, and then went over. That was the height of that rectangle. Now I'm going to use this endpoint, go up, and draw back. Because now it's going to be this right endpoint that's going to tell me the height. So now if we go to 2, go back. So far it's overshot.
You're counting both of those, right?
Say again?
You're counting both of those?
Yes.
Or would you start at F at 1.5?
Exactly. Good. So notice how the first time we did it, did we include the B? Did we include this?
No.
No, because I didn't need to. It was already caught by that rectangle whose height was determined by the point before that. So now everything shifts when I do all the right endpoints. Now I'm not going to include A. A dude doesn't define anything.
Because the 1.5 dude's got.
Because the 1.5 goes back and catches it.
Yeah, he's got
Right?
covered.
So now everything's shifted. Now I'm going to see 4 show up. But that's what I meant by you're going to see a lot of repeat function outputs. So it's going to make the computations easier. We're doing good so far?
Wait, how would you see a lot of repeats if it's
Because I'm going to see f of 1.5. It's really just shifted. Now I'm going to see all these, but now I'm going to also have f of 4 at the end.
well,
Because what's the height of the first rectangle? What's the height? What determines the height? Yeah, f of 1.5, right? And what's the height of the second rectangle? F of 2. So those are going to show up in my computation, and that's already here. So when you have to do a left endpoint, right endpoint problem, thank God it's not double the work, because you've already done a lot of the work in the first place. Okay, maybe. All right. So as always, some of you guys are bored already, and some of you guys are like, what the hell? I have no idea what's still going on. So this becomes pretty even, and then finally, there. So it overshot back here under. This one undershot here over. So that's why the averaging of the two should come out pretty close. Okay. All right. So to do this work, again, this should hopefully be pretty quick now to set this up. This will be 1/2. I'm not using 1, so I start at f of 1.5 plus f of 2 plus all the way up to f of 3.5 plus f of 4. Is that cool? Even though you can't see the whole areas. So it'll be 1/2 of 2 3/4 plus 4 plus 4 3/4 plus 5 plus 4 3/4, and f of 4 should be 4 because of the symmetry of the parabola. I love it. And then what you're going to end up getting is minus 1/2 that plus 2, so it'll be 13. It'll be 12.725. 12.625. That was close. Close ain't good enough, Jeff. Oh well. Sorry. So now do this. What's the average of those two that we got? The left and the right.
11.875. 11.875.
11.875? And now, if I'm you, I'm like, what the hell does that mean there? Okay. And I must have, when I first did this a few semesters back, I must have done this first. But I ain't like that anymore. So I'm going to show you how to do, actually I'm going to point 2 things out to you. I'm going to finally show you how to do derivatives on your calculator. Or actually, it'll just give you slopes at points. Right? So it's a really good thing to get a manual for your calculator. So you have to wait for me because I'm never going to show you in time. Except for now, I'm going to go ahead and show you how to do areas. Why not? So if I put this in here, let's go ahead and put this, if you have a calculator with you, because I didn't bring any, go ahead and put in there the function negative x squared. Oh, sorry. Well, you can still put it in. Yeah. Negative squared plus 6x minus 4 gather. What the hell is that? Negative squared. 6x minus 4. So the first thing I'm going to show you, and if you have never thought about what this might mean, you need to change your way of thinking. So when you look at second, and we've gone in here before, we did intersect and min and max. What else do you see there? Look at number 6. What's that? Slope. It's Leibniz notation for slope. So if I do that, if I say dy dx, and actually before we do this, let's try this real quick. The function is negative x squared plus 6x minus 4, right? What's f prime?
Negative 2x.
Negative 2x. So what's f prime of 2? 2. Just plug a 2 in, right? So if I say dy dx and I tell it 2, dy dx is 2. At 7, the slope is negative 11, blah, 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 blah. So this calculator cannot do symbolic algebra, which means it can't like factor expressions, but it can do numerical analysis all day long. So it can find derivatives at points. And it can also do, this is numerical analysis. It can eat this up. It can find areas under curves all day long. So of course, what would I use to do that? Well, you probably don't know yet, but it's that last one. See that symbol there? What's it basically look like? An S. But it's what you get. Let me go ahead and I've already kind of done this. Remember we said we're going to let the number of rectangles I use go to infinity? So then it would be the sum from I equals 1 to n, where n is going to infinity. F of xi delta x. When I let the sum become infinite, I replace this symbol with this symbol, which is just an elongated S. And that's really all it is, believe it or not. So that's what that means. That really means, intrinsically it means an infinite sum. And then you see at the end how it's got dx? Remember how delta x relates to dx? Delta x was big steps. Dx is infinitesimally small steps. And see what's going to happen, what's your width going to become when you let your rectangles become infinite in number. Infinitesimally small. That's exactly what that piece means. So it looks exactly like, and of course f is y. So the infinite sum of my function across delta x becomes integral of y dx. Oh, they did? Oh, I forgot.
Why is that y?
Just because. It doesn't have to be. It's f of x, which is y. I thought they had a y there. Thank you. So if I do 7, and it's going to ask me, where do you want to go from to? So I want to go from 1. And this is so kick-ass what it does. To 4. Shoop. You see that? Actually, it would be better if I did this. There. I know the key press is foolish. It would just give you a headache, but this is better. So, and what do they get? And what we get? Considering we only use 6 freaking rectangles, that's pretty close. And of course, it's because we averaged those 2 parts out. We saw that they should average out pretty close. Now, of course, if I use 12 rectangles, it's definitely going to get a lot closer to 12. And you can have this whole other analysis about how close do you want to be. It could be tolerance level and all that kind of business. Thankfully, we're not going to go there too much. We might go there a little bit. Stay with me now. Now, you might start to get interested, well, what would happen if I integrated this thing, if I found the area, let me use the right terminology here so far, of something that was purely underneath the picture here, underneath the x-axis. So like from -1 to 0. Look what it did. So And of course, I hate the fact that it leaves the old area up there. It doesn't like refresh. But this is the area it's doing right now. Notice how it didn't do what you might have thought. It didn't go inside. It's always between the function and the x-axis. That's how the integral is defined. And that should make sense, because how is my rectangle defined? The height is dependent on the output value. So my rectangles would be going from the x-axis down, right? So it should always be between the curve and the x-axis. And of course, my area is negative. So personally, the idea of a negative area does not bother me. It's the same idea as like a negative speed, which is really velocity. It just shows direction. In this case, it's showing me that that's below, right? So if I had like, let's do this. This will be the last thing we do.
So if you're asked for that area, the answer is actually a positive number. Even though
Depending on the way the question is asked. Yeah. Let's do sine x real quick. Okay, that's exciting. So if I integrate equally on both sides of the y-axis, so if I integrate from like negative pi over 2 to pi over 2, what should happen?
The area will be 0.
I love it. So if I integrate or find the area from, just plug it in there, negative pi over 2 up to pi over 2. The integral 0. I love it. Which makes sense. If this is my, how much my profit is changing over time, and I want to know from this point in time to this point in time how much money have we pulled in, it would be nothing, because it was going up from being negative, and then it's going down from being positive. Of course it should come out to be 0. So most of the functions we look at can handle the idea of negative area because it means something. And sometimes, depending on the situation, you are going to want to take an absolute value. Sort of like we did when we had that, how far did you actually go? And it was kind of like going back on itself. So you had to add it in an absolute value and all that kind of crap. Same thing sometimes happens here, but most of the time the functions we look at can handle it. In fact, they need that to be negative because it does mean I lost money in this case. Okay. I think that's as far as I wanted to go. Cool. Huh?
Do you mind if I turn this in?
No, I don't mind. I prefer you to do that.